Hello. In this lesson, we're going to talk about how to determine domains. And so we're going to cover these topics using the examples from your homework. Okay, first example is example number 1. I picked the question from your homework, which is f of x is equals to the square root of 4 minus x squared. Right there. Okay. To determine the domain, we need to understand that this is actually a composite function of square root and a quadratic function. So if we look from the simple perspective of a root of something, the square root of any quantity, then the input would be the omega, right? And omega produces, of course, an output, right? That's square root of omega. And this function has to have, this function has a specific requirement for the input. Okay, the input has to be at least 0. Okay, so this same model, we have seen this function, which is omega is going to assume the form of x. So square root of x, right? And x has to be greater than or equal to 0. So we have studied that function. So this observation, okay, this topic is always studied, right? We have input, which is a real number, but it has to be positive or 0. The output has to be a real number. So in this regard, to determine the domain, and we need to set whatever is being taken square root of. Okay, so this is omega, and this quantity has to be greater than or equals to 0. So this is how we would set up to find the domain. So there's always a model, right? From our simple function situation, that 4 minus x squared has to be greater than or equals to 0. And then we're going to solve this inequality. Okay, and apparently this is a quadratic function. So we can use, we have talked about many different techniques of solving quadratic inequality. And of course, we're going to use the simplest one possible, right? So we're going to have 4 greater than or equals to x squared, right? And or if you like, you can write it in this way, right? X squared less than or equals to 4, right? And then you take, either one is fine, right? It's just a matter of habit. And then we would take square root. We'll take square root of both sides. Okay. The left-hand side would give us the absolute value of x. And that's going to be less than or equals to 2. So in the end, our domain is going to be between -2 and +2 inclusive. Okay. So that would be the domain to this function. That would be the domain of this function. If you want to know how this function look like, a simple graph would, it'll show you a picture. This is actually a half circle. This is a half circle. This half circle with radius 4, right? If you're interested in, right? So you can get a picture at your fingertip. Right, so this is a half circle. And if you want to make it, if you want to observe it as the shape goes, you just try to make the shape, make the units to be comparable, then you can see it's a half circle. But anyway, so this is the domain of that function, this domain of this function. With any number in between -2 and +2, the output is always positive or 0, right? You don't need to graph to get the domain of this function, but having that visual would be helpful. Okay, So let's look at example number 2. Example number 2. And this one, I would use this function in your example, which is square root of 16 minus x raised to the power 4. To determine the domain of this function, of course, is the same model, right? So your setup would be whatever taken square root of must be greater than or equal to 0. And then you go about to solve this inequality and you get x raised to the power 4 less than equals to 16. And you take a fourth root, okay? Instead of square root, you would take the fourth root. Take the fourth root on both sides. On both sides. This is the even number root. This is even number root. And the left-hand side would be the absolute value of x, and the other side will be 2. Okay? And then we actually have the same answer as the one we did. And here I wish to review with you about the root issue, right? So this question now is done. So let's just do a little review about roots. We understand that x squared, when we take a square root of x squared, that's equals to absolute value of x. Cubic root. Okay, so let me put a table here. Okay, when we talk about even number root, okay, odd number root, if I have cubic root of x raised to the power 3, and that is equals to x. Okay, but if we have a fourth root, x raised to the power 4, fourth root, and this would be equals to the absolute value of x as well. And what if we have fifth root, right? If we have fifth root, x raised to the power 5, and this would be equals to x. Okay, and the table can keep going. Okay, what happened is that if the root number of 2, and this is 2 power 2, and this will be absolute value. So the same works for even number. So if you have 6th root and you have x raised to the power 6, and that will be equals to the absolute value of x as well. So if you have 7th root, so you see the pattern here. And the reason are similar to that for x raised to the power x raised to the power 3, and then taken cubic root. So these two are the representatives of their category. Okay, common mistake. The common mistake, which we have actually mentioned many times, is equals to x. This is a very, very common mistake. Okay, we have talked about this issue. Right? This is a common mistake. And some people have this statement. Okay, some people make this statement. What they say, okay, they say, oh, this is square root, and this is x squared, right? And so they take this 2 and this 2, they cancel them and they get x. If you learn this somewhere, I wish to tell you, this is a terrible mistake. This is a terrible mistake, okay? The right answer is right here, okay? The right answer is right here. Don't make that mistake, because you can see this relationship is used very often, very, very often. So if you make this mistake, you're gonna miss half the solutions. Okay, so don't make that mistake. So you have to understand why. Okay, so If you have any questions, let me know. Otherwise, if you need a review, go back to the week 1 and week 2 lessons regarding the absolute value and regarding the square root of x squared, okay? The other one is that the difference between, I wish to review with you, is the difference between the square root of x squared and the other expression, which is the square root of x, and then the square is outside. We have talked about this before, so let's review this once more. What is the difference between these two? What is the difference between these two? Okay, so I'm going to show you some couple differences. Okay, number one, right? So for this piece, that's one function, and this other piece, that's another function. Okay, from the flows perspective, right? If you look at the flow of operation, right? If you look at the flow of operation, right? For this piece, you're going to do x, and then you're going to do x squared, right? And then you do the square root of x squared. That's the flow, okay? And then you produce an output. Okay, so your output is going to be the square root of this piece, and that's going to be the absolute value of the x you start with. Okay, and this x, as a result, the domain right? The domain because the way we operate it, right? Because the way it's operated, x will be squared. After x being squared, and this x squared is going to be non-negative. So any real number after being squared is going to be non-negative. So it's automatically qualified to be taken square root. Okay, so the domain here is from negative infinity to positive infinity. But this other one, however, right? The input is x, and then you take square root immediately. Okay, and then after the square root is taken, and then we take the square of the square root. So you have to make sure the first step is validated. It can be carried out. As a result, this x has to be greater than or equal to 0. You can see the domain is, their domains are completely different. And the other thing I find it interesting, maybe we should look at the graph. Okay? So give you an impression, okay? So we're gonna look at the graph of each, okay? This is the graph of square root of x squared. This is the graph, right here, okay? How about this one? Look at this graph. Look at that, it's a straight line. It's a straight line, okay? Which is x. So I'm gonna make some adjustment. Okay, I'm gonna make some adjustment so that you can compare, right? And this way, I'm gonna put them in the same scale. So you can compare them side by side. So this graph is right here, right? That's for the absolute the square root of x squared. And the other one, okay, would be this piece. Okay, I'm going to make the scales comparable with the other one, which is also between -3 and +3. Make it kind of comparable scales, right? So this is the graph for that. And how do we graph them? You just plug points, right? According to the domain, you plug the points. So we're gonna omit that part. We're gonna omit that part. If you're so curious about it, just feel free to plot them yourself, the graphs. Right, so you can see these two are completely two different functions from the order of operation, from domain and range. Okay, so let's look at the range. And this picture, actually this picture, I think it's flawed. It's this function, this graph actually doesn't give this picture doesn't give the right graph. It shouldn't have this piece because the negative number is not in the domain. Okay, negative number should not be in the domain. So this graph should be, I'm going to manually correct it. Okay, I'm going to manually graph it. This should be the graph. Okay, this should be the graph. So this graph is just because of domain, right? Because domain, x has to be greater than or equal to 0. Negative x is not going to make it. Okay, it doesn't suit the domain. So these are the two functions, but this also shows the software I'm using is flawed. Okay, it's not designed as rigorously as it should be. So these are the two pictures for these two functions. Okay, for these two functions. And that's why in this case, it is always equals to the absolute value of x. And in this other one, it's x. But x is always greater than or equal to 0. So this will be the proper picture. Okay, the other one, the software is flawed. Anyway, so we've done some review, we've done 2 examples. So let's look at some more examples in the exercise. A lot of these exercises I actually pick from your calculus textbook. Okay, I pick them from your calculus textbook. So you might encounter similar examples when you are taking calculus class. Okay, so let's look at this function. F of x is equals to 1 over square root of x squared minus 3x minus 10. Okay, I need to make the fonts just a little bit larger so you can see the minus sign. Whoops. Whoopsie, 175%, 175%. Okay, so that's good size. Now, the square root part is in the denominator. It cannot be 0, right? So we have to set up, we need to guarantee the denominator cannot be 0, right? And also we have to guarantee that without the underneath the square root, this has to be greater than or equal to 0. So both conditions combined, we'll be left with that x squared minus 3x has to be what? Has to be positive, greater than 0. So this is a quadratic equation, a quadratic inequality. This is a quadratic inequality, and you can solve it in any which way you want, right? You can solve it by the sign, you can solve it by doing the function, the quadratic function, either way. Okay, so let's proceed as a review. How would you would have done it, right? So this is going to be x plus 2 times x minus 5. Seems factoring will be the easy way to go. And then you can work with the sign. Okay, so I'm going to take this opportunity to review these methods, right? These methods. The sign of x plus 2. Right, so where does it change sign, right? So some of you may like to set it equal to 0, and you need to understand why you set it equal to 0. You set it equal to 0 is to identify where the function crosses x-axis or where the sign change could take place. Okay, so this is the purpose. This is the reason you set it equals to 0. Okay, make sure you understand that. Okay, So you would have x equals to -2 or x equals to 5, right? So these two numbers, right? -2 is where x plus 2 changes sign, and before -2 and after -2, right? So we're gonna work on the sign. So here we have -2, right? And before -2, of course, I don't need to make it too long. Before -2, I mean, this expression as a function, it defined on the entire number line. So you have to look at the sign distribution on the entire number line. So when x is less than -2, so you pick a -3, you plug in, and you're gonna get a negative sign, right? And at -2, if you plug in -2, you're gonna get 0, right? You're gonna get 0. And after -2, if you pick a number larger than -2, say 0, right? 0 is larger than -2, you're gonna get positive numbers. So this is the distribution of sign for x plus 2. You can see x plus 2 changes sign from negative to positive at -2. So -2 is a turning point. Okay, x equals -2 is a turning point. So we do similarly of x minus 3. I'm sorry, x minus 5, right? X minus 5 changes signs at 5, right? So at 5. So here you go, you put a 5. It doesn't have to be proportionally perfect, right? You just have to mark it properly. And when you choose a number less than 5, so you choose number 4, and this expression is going to be negative. When you plug in 5, it's going to be 0, right? It's going to be 0. And after 5, you plug in the number, say you plug in 6, 6 minus 5 is positive, so you're going to get a bunch of positive number, right? So that's the distribution. That's a distribution. And then lastly, you look at the sign of the product, right? The product of x plus 2 times x minus 5. Okay, I hope this is a proper review for you. And you're not too bored about watching and seeing this again, right? So we have a -2, so we have them line up. And we have a positive 5, so we have them line up, right? So we line them up, right? So -2, positive 5, right? And the sign distribution. Sign distribution, basically you can see I have lined up all these -2s, right? All these 5s, okay? So if I pick any number from smaller than -2, right? And I plug in these numbers into this expression, say I pick up a -5. -5 plug in here, I'm gonna have a negative number. -5 plugging here is -5 minus 5, that's going to be negative. So negative times negative is going to be positive. So on this piece, the product of these two numbers is going to be positive. 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 At -2, at -2, and this expression is going to be 0. 0 times non-zero is going to be 0. Okay, between -2 and 5, if I pick a number, right, I can pick a, any number I want, and I plug in, I will end up with a positive times negative. Positive times negative is going to be negative. At 5, when x equals 5, x minus 5 is going to be 0. So 0 times a positive number is going to be 0. And for numbers larger than 5, so I'm going to pick up another number again, right? So I'm going to pick a number right here, larger than 5, and I plug in, I have positive times positive, right? So this is going to be positive. Okay, So this is just to consider the sign distribution, And what do we want? What do we want? We know the sign distribution of this product. What is wanted? What is wanted is that we want the product to be positive, right? So the solution, so where do we give positive? So solutions to this positive requirement we have here, which is determine the domain, is that when is this product positive, right? So over here or over here. So the solutions would be x less than -2 or x is larger than 5. So that will be the solution. Okay, you can put them on the same row. So now you can see everything being together, So we really just observe the sign, applying principle number 6, right? And this method is used very often. Okay, the other method I like to review with you is method 2, is treating this as a function. Okay, treating this as a function. Of course, they are functions, right? And you will still need to find so I'm going to copy this piece over here. Well, you still need to do the things, but you know the purpose. So I'm going to treat this as a function, right? I'm going to treat this as a function in my mind. I'm treating this function, right? I'm setting this equal to 0. This is to do what? This is to identify the x-intercepts. And here we have 2. Okay, this is to identify x-intercepts. Okay, so we have identified our x-intercepts. So what are the x-intercepts? So the x-intercepts are, you can see how consistent, it's just really different interpretations, right? So the x-intercepts are -2, 0, and the other one is 5, 0. It would be so relevant because as we see this as a function, right? And you can graph it, right? You can graph it by hand if you want, right? You can even determine the vertex by yourself. Wait a second. So let me graph it. That's more like it. I think I would just copy and paste something I had earlier. Okay. So this is the graph, and I'm going to make some adjustment. Okay. So let's see. I'm going to have, say, -4 here, maybe 7 there, right? -6 and 10. I just randomly look at these numbers, put these numbers. If it doesn't work, and I just adjust it. Actually, even this picture is fine. Why? Because all I need to determine which piece is a positive. And this picture obviously is not quite complete. I can make it more adjustment if I wish, right? But you don't have to see the vertex because you already see this is a positive piece, this is a positive piece. Okay? To get that perfect picture, you have to do some more adjustment. There you go. It doesn't have to be perfect. You just have to identify the positive piece and the negative piece. Okay, so the x-intercept here now has a place in the picture. Okay, so I have a picture here. The red dot. Should I have dot or circle? I think we should have circle. Let's have circle first. Okay, I will explain to you why we need to have circles. Okay, why we should have circles? Because we want the product to be positive, does not include 0. So the piece that gives us a positive product is this piece, that piece. that piece is negative. And this circle at the point of circle, which these 2 points are, it caused the output to be 0. And we don't want the output to be 0. We want the output, we want the product to be positive, not equal to 0, right? So that's why, so you have that input output concept. Okay, and the numbers outside less than -2 or bigger than 5. So we're going to mark those intervals. Okay, we're going to mark those intervals, and you will see right, you will see it's absolutely consistent. It's absolutely consistent with what we have studied. Okay, so these 2 pieces, okay, these are the 2 pieces for these input, right, from the, any point marked by the red, and their output will be positive. The output, of course, will be the product or the function. Okay, so that's what this picture means. Okay, I hope that's sufficient review for you. And if you put these 2 pictures together, okay, so let's mark the solution. So the solution to that greater than 0, right, are x less than -2 or x is larger than 5. If you put these 2 pictures side by side, right? So this is the afterwards, okay? Afterwards. Okay, you don't have to show this, but just for your own comparison. If you put this picture, okay, side by side with this piece, okay? You put these side by side. 2 different methods, right? What do we see? What do we see? We see exactly the same thing, right? For these inputs, the output are positive outputs. So all these different methods, they are absolutely consistent in principle. Okay, it's just some are written this way, some others are written other ways. The textbook uses the table method, which is also conveying the same idea. You can make this out of a table. You can make this whole idea out of a table. Okay. All right. So consistency. Okay. So let me just move this a little bit over here. You can see that I'm trying to get the 5 line up and the -2 line up, and that's it. That's it, right? So we got it. So that's one example. I want to say something about number 7. So this is going to be our example number 4. Okay. Example number 4. This question actually was from a calculus textbook. Okay, is the textbook you are going to use. Square root of 3 minus x minus the square root of 2 plus x. To determine the domain, we have two separate square root, okay? And each must be made meaningful. In other words, we need to guarantee the domain for the requirement for both are satisfied, okay? So the setup, right? You look at the individual, right? 3 minus x under 1 square root, and that has to be greater than or equal to 0. And there's another one, which is 2 plus x is also under another square root. This has to be greater than or equal to 0. And these two must be connected somehow. And these two must be connected by and. It means that both conditions must be satisfied at the same time. At the same time, okay? So we're gonna solve these two inequalities, and from the first one, we get x less than or equals to 3, right? You just add x on both sides. On the other one, you get and x is gonna be greater than or equals to -2, okay? And then you're gonna combine these two requirements. To do that, you would, you know, I'm gonna draw a picture to show you how would you determine that. Okay, how you would determine that. Okay. We're not drawing any picture, right? So we're just going to we're gonna make a number line. We're gonna make a number line. Okay, so we have a -2, we have a +3. So this is the number line we're talking about. So -2 is here and +3 is over here. So we're gonna combining these two conditions. So first we're gonna identify these 2 points. Okay, these 2 points. One is 3, it's a red dot because it's less than or equal, right? And the other one is -2. So we have these 2 dots. We have these 2 dots, okay? Less than or equals to 3, meaning, right? Less than or equals to 3, meaning all of these numbers. All of these numbers are less than equals to 3. Let me not put this away, okay? So all of these are less than equals to 3. Larger than or equal to -2. So here's -2, larger than or equals to -2. Anywhere that's been marked twice, meaning the condition is being satisfied twice, meaning the conditions are, both conditions are satisfied. Anywhere that's marked only once, meaning that only one condition is satisfied, but the other is not satisfied. So we want the part that both conditions are satisfied. That's the meaning of and, because and can be true if true and true, right? And A and B is true if both A and B, both A is true and B is true. So this is A, this is B, right? Look at the truth table. So as a result, where is being marked twice between -2 and +3. So in the end, the domain we have determined okay, is -2 less than equals to x less than equals to 3. So that would be the domain. That would be the domain. Okay. So that's how you determine the domain. So now I'm going to make it like a real number line. Okay. I'm just making some adjustment for this using the software. And you can ignore the y-axis, right? So this is the number line, and I'm going to mark it in between. I'm going to mark it in between. Okay. Oh, well. This software doesn't graph one-dimensional. So now I'm just going to mark the interval. Okay, in which the domain, okay, that shows the domain. So that's the picture. And these inequalities is always the preferred form. Okay, at least for me, it's a preferred form by me. Because they tend to be more useful. They tend to be more useful, okay? But this make a great effort to learn how to use it, okay? I think you can handle number 8. So let's look at number 9. Okay, number 9, that I'll make it example number 5. Okay, so we're gonna find the domain of f of x equals to, we have 2 layers of square root. Okay, so 2 minus the square root of x. 2 layers. What shall we do? What shall we do? Well, you have to look at, there's this layer, right? If you look at this as a one entity for the square root, right? To set up, you have to guarantee that this piece underneath the square root has to be greater than or equal to 0. But at the same time, there's a square root of x right there. And this piece has to be, for this piece, right? For this piece, it has an entity underneath the square root. So this x has to be greater than or equal to 0 as well. And to connect them, we have to connect them by and. So both must be satisfied. Both must be satisfied. And this inequality is already solved. We just have to solve this inequality. So how do we solve this inequality? So we're going to solve adding square root of x on both sides, right? So we have 2 greater than or equal to square root of x, right? And then how do we find the x, right? X is already greater than or equal to 0, so we can square both sides. We can square both sides, right? Square root of x actually is an increasing function, if you recall that curve we did. So we square both sides. As a result, we get 2 squared greater than or equal to square root of x, and that being squared. What does this guy equals to? We reviewed that concept earlier, right? We reviewed that concept earlier. The square root of x and then squared equals to x. And so we're going to apply that. Okay, so the next step we get is 4 is greater than or equals to x. So now we're going to combine, okay, combine these two. Combine that x is less than or equals to 4 and x is greater than or equal to 0. Okay? What would that be? What would that be? If we take this number line, okay, I'm going to clean it up, right? I'm going to clean up. Right? Less than or equals to 4, greater than or equal to 0. So this is 0, there's a 4. And we will have a similar situation, isn't it? 0, 0. So we make it a red dot, right? And the other one is a 4, 0, right? 0, 4. And less than or equals to 4. This is a 4, less than or equals to 4. It will be all of these until negative infinity, right? Greater than or equal to 0. So I'm going to mark them by star. All of these, all the way to positive infinity. So wherever they marked twice, and that's the place, those are the X values that satisfy both conditions. And those are the numbers between 0 and 4. Okay, so needless to say, in this situation, all the numbers that we're looking for are going to be between 0, right? 0 less than equals to X less than equals to 4. So on the graph, you can see that interval can be marked by a red marked thicker interval indicated like that. Okay, so once again, this interval is in inequality form is preferred, and it tends to be very, very useful. Okay. I will do number 10 for you because it has a little more complexity, It's very similar. So example number 6, and we have a function. Well, this actually is from your textbook, calculus textbook. Okay, so 1 minus square root of 1 minus x. We have 2 layers. Okay, so the setup is very similar to what we did earlier. It's just solving the inequality part, right? So setup is absolutely important. You view this piece as underneath the square root. So this piece has to be greater than or equal to 0. And of course, you know, we're gonna use and. And the other piece we need to observe, which is also underneath the square root, is 1 minus x. And this has to be greater than or equal to 0. So you have 2 inequalities, and we have to solve them in parallel and then combine them. So the first one, if we add the square root part, we're going to have 1 greater than or equal to square root of 1 minus x, right? And of course, we're going to maintain that relationship. We don't combine them yet. And over here, you add x on both sides, you end up with 1 is larger than equals to x. So this part is already solved, okay, which is the same as x less than equals to 1, right? But this part requires a little more work. So what we do here is that we're going to square both sides. Both sides are non-negative, okay? Because this piece, you know, they're going to satisfy the domain requirement. Domain requirement is already satisfied. So we can square both sides. So we get 1 squared, 1 squared greater than or equal to, and this piece is being squared. Okay. And the other piece, we're going to just, we just keep it like that. And you can, if you like to write it in different ways, sure, this way, right? X less than equals to 1. So this is the same. These two are the same. But this way of writing it seems to be more conventional. And now we get, on this inequality, we get 1 greater than equals to 1 minus x. Okay. And then what? And then what? We don't add x on both sides, and 1 reduced, right? So what do we get? We're getting x is greater than or equal to 0. X greater than or equal to 0. So what you do? Well, you subtract 1 on both sides, right? And then you add x on both sides. You get x greater than equal to 0. And this piece and x is less than equals to 1. Whoops. I'm obviously clicking the wrong thing. Okay. So now we're going to combine these two. Combine. What are we getting? Well, we're getting x is greater than or equal to 0, less than equals to x, right? 0 less than equals to x, and x is less than equals to 1, right? It's very similar to what we did earlier. So the domain for this function is really just this little piece. It's really just this little piece, okay? So if you're curious, you can graph it, okay? I'm going to save that for you. The next piece is, I'm going to call it example number 7. And this is your homework number 11. Okay, still determine the domain. This is actually exactly a question from, or after you've done some work, after you take a derivative of that function that you're going to take in your calculus class, and you're going to end up something like this. Oops, x squared, and you have a square root underneath. Okay, so how do we set up? On this piece, right, you have 2 minus x squared. It has to be at least 0. On the other piece, which also has to satisfy, right, underneath, where you have, this cannot be 0, right? This whole thing cannot be 0, right? So greater than or equal to 0, you can only have positive, right? And, right, so underneath the square root, both need to be greater than or equal to 0, but it cannot be 0. As a result, the consequence of combination is that you're going to have 2 minus x squared larger than 0. Okay, so now you end up solving this inequality. Then you add x squared, so you have 2 larger than x squared. Okay, take square root on both sides. If you like, if you like to write it this way, that's fine too. It doesn't matter. Okay, it really doesn't matter. And then you take square root on both sides. Okay, so I'm going to call this AKA, right? Also known as, okay? Optional. So we're going to take square root, and you have, don't forget, this is absolute value, okay? Less than square root of 2. Okay, so in the end, you will have x between negative root 2, okay? Great. Less than square root of 2. So that's the domain. Okay. And so here we have one example of logarithm. I'm going to make this example number 8. Okay. The function in consideration is natural log x plus 2. Okay. I want to put a note here that this function is different from ln x plus 2. They're different. They're completely 2 different functions. Okay. For your information, this is very important to understand. Okay. So this piece versus this piece, they're completely different in domain and in flow. Okay. So I'm going to show you the flow of operation. X is the input, and this piece X is the input, right? They both are X are the input. But this one, you'll be given to the function machine ln x right away. And you get out as the output. And after you get this output, you take ln x, u plus 2. That's the order. But this one, however, you have to do x plus 2. And after you do x plus 2, and then you apply the function, which is ln x. Okay, you're going to take ln x. You're going to use that ln x. So you come out ln x plus 2. And this is done first. So parentheses is done first. Okay, so I'm going to use the same machine. It doesn't really matter because it's just symbolic. Okay, symbolic. So you can see they have different flow. Do they have the same picture? No, they don't have the same picture. They have a completely different picture. Okay, so this is the picture of ln 2. No, this picture is not complete. I need to make adjustment. Okay, x must be positive. Okay, so the domain so let's see. That works. Maybe I should give it 5 or 6. Okay, just to make sure we have a proper picture. So this is the curve for ln x plus 2. It's actually ln x is shifted up by 2 units. Okay, so this is the picture for ln x plus 2 without the parentheses. Okay, so this is the picture right here. Okay, that's the picture. Okay, how about with the parentheses? You're going to see a completely different picture. They don't even have the same domain. They don't have the same domain. So we're going to discuss this. I'm going to use this opportunity to discuss this. Okay, so the domains are different. So this is negative, let me put -3 here. Okay, 8, -2 over here, make it 6. I try to make them the same scale. There, and put the same picture. And we're going to make them the same scale so you can see for yourself, right, how different they are. Now they don't have the same scale, right? So here on this one, I'm going to adjust it to -3 to 8, right? So -2. So the vertical direction is correct. You can see they're different. Their vertical asymptotes are different. This vertical asymptote is the y-axis. Okay, so if I'm going to draw the vertical asymptote for you. Oops. Okay, that's the vertical asymptote. I'm going to make it a red broken line, a little bit thicker, medium. So that's the vertical asymptote. On this one, you can see that the vertical asymptote is at a different place. Okay. Here's, oops. And here's a negative, I'm going to also make it red, medium, and broken. You can see the vertical asymptotes are completely different. They have the same range, but they don't have the same domain. So the domain, so now let's talk about the domain. Right? the domain on this one obviously is x is greater than 0. On this one is x plus 2 must be greater than 0. As a result, x must be greater than -2. So you can see that rather obviously. Okay, so these two are different. Okay. Other than that, this question is pretty simple. It's pretty simple. And for the remainder of 6 questions, they're trig functions, and you will see why we solve inequalities, trig inequalities, right? Because there's such a necessity. Okay, so the remaining two questions to determine the domain. So let's look at this should be example number 9 or 10. Number 9. Okay. So solving trig inequalities. Okay, so we have a function right here that equals to cosine x 1 minus sine x. Okay, we have to set up that inequality, but there's 2 ways to express this. Okay, being aware, right? Being aware that we're to determine the domain, we can set it up. We can set this equals to 0. This is a common method, but you need to understand that when you set up equal to 0, you're going to get solutions, and those solutions cannot be in the domain. Okay, so that's something you need to be aware of. Other than that, that's just the rest is it's technique, right? Sine x equals to 1, and x has a domain of all real numbers. So what are those numbers that will make this true? And that will be, the multiples of pi. I'm sorry, pi over 2 plus 2k pi, where k is integers, can be any integer, right? So you can use unit circle that come to your rescue, right? You can use that unit circle to demonstrate this, right? It's just sine x cannot be equals to 1. So you look at the blue numbers, right? Which blue number give you 1? Right here, there's a 1 and only, right? But this terminal, you should identify the terminal. That terminal is right here. So this whole thing is a terminal. You don't have to bring the entire unit circle with all these accessories with you, or you just simply use a rectangular system to demonstrate that, right? You just identify one terminal, right? DRA, and the angles will be pi over. Then you measure the angles from standard position, clockwise and counterclockwise. So this expression basically shows you all the angles could possibly be that terminate on this terminal. That is forbidden. That's forbidden because we don't want that to be the input for the function. If those answers as an input, then domain, we will have 0 as a denominator. So in the end, in terms of domain, you would express it as x is not equal to, so equal turn into not equal. So that's the logic behind this. That's a domain, right? So any number make it equal to 0, they cannot be in the domain. So the meaning of this statement, okay, meaning is any real number except all of these. So that's the meaning. And we write it in the shorthand notation like this. Okay, so we use that shorthand notation. number 14. That makes that number, example number 10. Okay, the function in our consideration here is 1 over tangent x, 1 minus tangent x, sorry. Oh, sorry, I forgot another way to set up for the previous question, okay? So this is one way to set up. So let's make it method 1. I do want to talk about the other method. The second method to set up, for the same question, sorry. Okay, the second method to set up for the same question is actually has a little minor difference, right? Is that you set up as, okay, 1 minus sine x not equals to 0. Okay, that's the only difference. And then you go about to solve this inequality. So you the whole time you're thinking, okay, I need to find those values, sine of x not equals to 1, right? So x cannot be, so you're thinking the opposite of it. So you still get the same answer, right? Not equals to pi over 2 plus 2k pi, right? Where k is integer. So these are the two different setup. To me, either way is okay. Either way is okay. You just have to be aware. And in this case, your domain is right there. You don't have to make a special line to say, oh, domain, you have to write the opposite of it. So your domain is already here. Your domain is already here, right? So you just have a little less to write. Okay, so in terms of logic, or these are the two different ways of setup. So this one, the same thing, right? So you set up, and it cannot be, well, you can set it equal to 0. This is the most common. Okay, this is the most common. I'm sorry, this is x. Okay. And then you solve this equation, tangent x equals to 1. Do we know how to solve this equation? Right, obviously this is related to a special angle, right? This is related to a special angle. But tangent x equals 1, where could it be? And we can bring back our unit circle. Okay, or you can work with your, rectangular system. There are two ratios, right? Y over x that will give us those ratio equals 1. So 1 is here, 1 is there. So you have a terminal, which is, this one is a terminal. There's a terminal here, and there's a terminal there, right? And here you go. You identify the terminal, DRA, right? From D, you identified R and A. So in the end, your x would be pi over 4 plus k pi. Plus k pi. And of course, k is any integer. K is any integer. Okay, so in the end, when you express your domain, you would say all of that, right? And change the equal sign to not equal. All real numbers except, right? The meaning is that it's all real numbers except what? Except these numbers that cannot be in the domain. Okay, for the other way of setting up you can also work it out. You can also work it out. I like to mention number 16. Number 16 looks a little, you know, let me make this example number 11. It's actually not that hard. Okay. Example 11. So this function in our consideration is equals to cosine x over 2 plus sine x. I want to use this example to demonstrate to you that knowing the domain and range of sine can be so useful, and knowing how to use them is even more useful. Okay, so you can set up, right? But the thing is that if you set up, I'm going to give you two versions of the solution, okay? If you set up like this, right? You say, okay, I'm going to set it equal to 0. I'm going to solve for it. Sine x equals to -2. And then you realize, wait a second, do we have a solution? No, we have no solution here. Because this will never happen, right? Why there's no solution? Why there's no solution? Because sine x is always between, the output of sine is always between -1 and 1. So this will never have any solution, right? So that's a domain and range in one sentence for sine, right? So for any real number x, and therefore this will never happen. Okay, so this is the first, this is one of the ways you do is if you get into that autopilot, say, okay, I'm going to set up, denominator cannot be 0, you will find your way, you'll find your solution. But I do want to show you another way to do this, is that you are being aware. You are being aware of this, okay? So you realize that because of this domain and range for sine, okay, you can say because, okay, 2 plus sine x is always going to be positive. So it's always going to be positive. Okay. And therefore, you never have to worry about, because this will be true for any real number x. And therefore, the domain is what? All real numbers. All real numbers. No number needs to be excluded. And that's the same for the earlier interpretation. No solution means that the domain is all real numbers, meaning no number needs to be excluded. As we're doing this, I want to give you a third version of this. So hopefully this will help you to know how to manipulate, right? So from this condition, from this situation, okay, I'm using the same inequality. So I'm going to take this piece. I'm going to take part of it, right? Taking part of it, I know this is always true. So what I'm going to do is I'm going to add a 1 on both sides. I'm going to add a 1 on both sides. Okay, this is just a, trivial algebraic manipulation. So I got 1 plus sine x on the other side. So 1 plus sine x is greater than or equal to 0. Now, if 1 plus sine x is greater than or equal to 0, what happens if I add another 1 on both sides? What if I add another 1? So I'm going to add another 1 on both sides. What will happen? So I will have 1 is less than or equals to 2 plus sine x, right? What does this tell us? This tells us that as a denominator, which is 2 plus sine x, that quantity is always going to be greater than or equals to 1 for any real number. Okay, this is true for any real number, and this is true for any real number. And therefore, we never have to worry about having a 0 in the denominator. Therefore, the domain is all real numbers again. But these little, it seems pretty trivial techniques. Okay, practice with these, how to handle inequalities. It's going to benefit you tremendously. It's going to benefit you tremendously. Okay. Last but not least, now we make a dozen, right? This lesson is to identify the domain for this function. This will be an interesting function for you. Okay, we have a square root of 1 plus sine x over 1 minus sine x. Okay. First thing first, okay, so we see this as, if you see this as, oops, if you see this as a giant taken square root of something, and this piece, which is that, has to be greater than or equal to 0. Okay, so in your setup, you need to see that as greater than or equal to 0. And of course, that's not all of it, right? This quotient has to be greater than or equal to 0. But we also have to make sure that the denominator cannot be 0. Okay, the denominator cannot be 0. Denominator cannot be 0. Okay, is there any other conditions that we need to consider? Right, so the flow is that you have input for x, right? But you also have to, you may like to also consider that sine x is always between -1 and +1, okay? So all of these is in your mind, right? So you may like to have a little reminder, right? Sine x, where you want to use the other form, right? Sine x is always between -1 and 1, right? Just have these forms, at your disposal, so you don't run the risk of forgetting them and get lost. Okay. There you go. So I'm just put this as a side note, maybe on my scratch paper. Okay, but this looks a little bit complicated, but no fear, right? So we need to guarantee this cannot be 0, and we certainly know how to solve this one. We have done that before. We've done that before. So this is n part. Oops, this is the n part, right? I already know how to solve this piece, right? So we have done that. So x not equals to pi over 2 plus 2k pi. So the not equal to 0 issue is resolved. Okay, not equal to 0 part is resolved. And then we're going to focus on solving this inequality. Okay, so now we're going to solve this inequality. Okay, so we're solving this inequality, and with the guarantee the denominator will not be 0, right? So this is guaranteed. Okay, and we want this to be solved. Can we multiply both sides by 1 minus sine x? Can we do that? Can we, well, before we do that, or we think about, maybe we like to do that, let's look at the sign. Okay, I always say that this condition is crucial. This fact, I would say not, it's not a condition. This fact is crucial. From this crucial fact, right, we can derive a lot of things, right? Half of it from here, right? From this piece, right? We know that this is true for what? This is true for any real number x, right? And what does that mean? Of course, part of it is also true, right? Yes. So this will give us the opportunity. If I add 1 on both sides, I will have, oops, sorry. So I'm going to add a 1 on both sides like we just did this earlier, right? If I add a 1 on both sides, you can see this is pretty fun, isn't it? So we ended up with 0 is less than equals to sine x plus 1. So 1 plus sine x, which is the numerator, is always positive or 0. Okay, this numerator is always a positive or 0. Okay, so let's look at the other half. Let's look at the other half, right? So from the other half, right, which is true for all real numbers, but from this half, what would you like to do? From what's been given, you would subtract sine x on both sides, right? Because you want to get in something like this, right? So you're going to subtract sine x on both sides, right? So you're going to subtract sine x on one side, subtracting sine x on the other side. And what you get? You get 0 less than equals to 1 minus sine x. And of course, we don't want it to be 0, right? Under these circumstances, it's not going to be 0. So you have a situation like this, right? We want it to be greater. We wanted, this is wanted. This is wanted, right? And we also have this being guaranteed that the bottom is not 0, right? With, right? So, and now you can see the denominator is always going to be positive under this condition, right? So you have a situation, the denominator is always positive, right? The denominator is a positive with this guarantee, right? The numerator is always a positive or 0 for any real number. So with this additional condition, of course, that's always. So this is going to be positive or 0. So what will be our conclusion? What will be our conclusion? With that, that will be our domain. Okay, so the domain is just going to be what? This piece. That's it. That's it. You can see how useful this piece is, right? It is always true. It's always true. So we just add a little additional condition to guarantee the denominator is not 0. And we're good. So that, sorry. Okay, so that would be the domain. Okay, I think this example demonstrates to us that some of these facts are so crucially important and incredibly useful in many applications. As a matter of fact, you're going to find more applications of this amazing fact in your calculus classes. And not many chapters into the semester. Probably the second chapter, you already start seeing this being used as a very useful tool for you to, to demonstrate, to use it, okay, to get points, okay? So make sure you understand those domain and range. Without further ado, I think this lesson, we covered 12 examples. That's plenty. And we do have other lessons in this week that we have solved the equations, we've solved inequalities. Solving inequalities has always been pretty tricky, okay? Because you can see when we solve inequality, we always use principle number 5 and number 6, especially number 6, okay? With these two principles, when we solve inequality, okay, our typical steps, let me put a little summary here. Our typical steps, right? So we ended up solving inequalities, right? We're trying to find domain. And we often end up solving inequalities. That's what happened, right? We tried to find domain and we ended up solving inequalities. Okay, and our guiding principles to set up is that you look at those basic functions. So what are those basic functions, right? So what help us to set up, right? You look at the basic functions. So what are the typical basic functions we're talking about, right? Some of these functions may be the square root of x, right? Some of those functions may be the cubic root of x, right? It could be 1 over x, right? These are the basic functions to help us decide the domain and range. And logarithm, any base, right? X, right? And their typical examples is ln x, right? And yeah, all these basic functions, I'm just naming a few, are guiding our cases, guiding our setup, right? And because underneath all of these axes would turn into omega, which could turn into complicated expressions, as we saw in these examples. So they're not just a singular variable. It could be a complex expression. So when we set them up, like in these examples, right, we view it as a omega, but this omega is 4 minus x squared. It's more complicated, right? In the logarithm case, so you need to consider the requirement, and those requirements often comes from the basic function. And then you end up solving inequalities. So for those basic functions, you really have to know their domain in inequalities, right? So you need to know the domain of those basic functions in inequalities, right? If you only have interval, it's pretty hard to solve. It's pretty hard to work with. So only when you set up as inequality, and then you can maneuver algebraically and then in the end to solve it, right? Right? Imagine that you use imagine that you use this interval. You say, oh, I'm going to use interval to express, say, for example, you're going to say, okay, the interval expression for this piece, right? So 4 minus x needs to belong to this interval, which is from 0 to infinity. How are you going to solve that piece? How are you going to solve that? You still have to transform it into inequality to solve it, right? So that's why the interval notation is good, but not always useful. They're good, but you have to know the inequality form to work with it. Okay, so that's my point. Okay, so that is my point. You must know the inequality forms, right? You can see this one too, right? How would you work it with interval, right? How would you work it with the interval? On the interval form, then you're going to have, 16 minus x to the power 4, right? You tell the reader, hey, this is going to be belonging to 0 to positive infinity. And then you're going to solve for x. How are you going to solve for x? You still have to transform it into inequality to solve it, right? And the same can be said about, these things, these inequalities, right? The same can be said for these inequalities. You can say, oh, this piece, right, is going to be belongs to this interval from 0 to infinity. That's no problem. But how are you going to solve this? You see, you still have to transform it into inequality. Make sense? I hope that makes sense to you. So you're going to practice how to solve inequality. They're very much needed. They're very much needed technique for you to solve inequalities. Okay, so all of these examples, if you go over them, then you realize, yes, solving inequalities is a much needed technique. Okay. So that's why I emphasize the use of inequalities. Emphasize the use of inequalities. So please really make those efforts to try to work them out and express them well. And you will need that. You will need that. Okay. So without further ado, I think this lesson is long enough. And I will see you guys next time. Thank you for watching.